The atom is made up of three different types of particle: protons, neutrons and electrons. The central part of the atom is called the nucleus. The nucleus contains neutrons and protons. Protons have a positive charge and neutrons have no charge, they are neutral. Each nucleus is orbited by electrons. These have a negative charge and orbit in shells. It is the attraction between the positive protons and negative electrons that keeps the electrons in orbit. All atoms must be neutral. This means that the number of protons and electrons must be equal. Notice that all atoms of the same element are identical, but those of different elements will be different. All the atoms in a piece of glass are neutral. There are equal numbers of positive and negative charges. If a cloth is rubbed across the rod, energy must be supplied to overcome the frictional forces acting. This energy is given to the electrons that jump across to the cloth. The cloth has gained electrons and becomes negatively charged. The glass rod has lost electrons and becomes positively charged. Both objects have become charged with static electricity. A polythene rod. A polythene rod can also be charged by rubbing with a cloth. This time electrons are transferred from the cloth to the rod. The polythene rod becomes negatively charged and the cloth becomes positively charged. If a positively charged glass rod is brought close to the suspended negatively charged polythene rod, attraction occurs. Oppositely charged rods attract. If two positively charged rods or two negatively charged rods are brought close together, repulsion occurs. Like charges repel. The size of the forces. The force between two charged objects is increased if the size of the charge is increased. The animation shows a suspended positive ball being repelled by a small positive charge. The balls repel weakly. If the charge is made larger, a far larger repulsion force occurs. The size of the force also depends upon the separation of the two objects. As the positive ball is brought closer, the suspended ball is attracted more strongly. Induced charges. A charged polythene rod will attract a small piece of neutral paper. The paper has equal numbers of positive and negative charges. As the rod approaches, electrons in the paper are repelled away. The top of the paper becomes positive and attraction occurs. We say that the top of the paper has a positive charge induced on it. Induced charges can also explain why a positively charged balloon will stick to a neutral ceiling. Electrostatic paint spraying. The car body panels must be sprayed evenly. The paint gun is charged negatively and the car panel positively. The paint droplets are negative. They repel each other, producing a fine, even spray. The paint is attracted only to those areas of the car that are charged positively. Electrostatic smoke remover. Smoke and dust particles can be removed from factory chimneys before they reach the atmosphere. Inside the chimney there is a metal grid suspended between two curved plates. These are charged positively and negatively by applying a very high voltage. Smoke particles are charged positively as they pass the grid. The particles are attracted and stick to the plate. Refueling aircraft. Aircraft must be refueled quickly. This requires the fuel to be pumped at high speeds. The fuel can become charged by friction with the pipe. Sparks can occur, resulting in explosions. This is prevented by connecting the plane and the refueling tanker by a conducting copper cable. The tanker is then earthed for added protection. Drivers sometimes experience an electric shock as they get out of their vehicles. This happens when a vehicle has become charged during the journey. The charge flows through the driver to earth. Some clothing becomes electrically charged through the day. When clothing is removed, discharging occurs and a crackly noise is heard. Dust is often attracted to TV screens. The glass front of the TV becomes charged when in use. Metals are good conductors of electricity. A metal contains charged particles called electrons that are free to move throughout the crystal. If a battery is connected, the electrons are forced to drift through the metal. The electrons are repelled by the negative terminal and attracted to the positive terminal. The battery acts as an electron pump, forcing electrons around the circuit. We call this flow of charged particles an electric current. Electron flow and conventional current. We know today that an electric current flowing through a metal wire is a flow of negatively charged electrons. However, the early experimenters guessed incorrectly. They thought that an electric current was a flow of positively charged particles flowing from the positive to the negative terminal of the battery. We still use the positive to negative current direction in all our circuit diagrams today. All scientists have agreed to do this. We call this the conventional current direction. Complete circuits. In order for the current to flow, we must have a complete circuit. This means that there can be no breaks in the connecting wires. If the wire is cut, no current leaves the battery and no energy is delivered to the lamp. Conductors and insulators. This simple electric circuit can be used to show that non-metals are poor conductors or non-conductors of electricity. Metals contain moving charged particles and allow a current to flow through them. Non-metals do not usually allow charged particles to flow through them. Graphite, however, is an exception. Its structure does contain free-moving electrons. Circuit components and circuit diagrams. All circuits contain devices that make the circuit work. These devices often perform energy changes or are used to control the current flowing. We call these devices circuit components. Each component has its own symbol and performs a certain role in the circuit. The lamp provides light. The battery supplies the current with electrical energy. The switch opens and closes the circuit. The buzzer produces sound. The variable resistor changes the current. The motor rotates, producing movement. The components can be connected to form a complete circuit. This circuit can then be represented by a circuit diagram. The circuit diagram does not show three-dimensional pictures of the components and is much easier to draw. Measuring current. We can measure current using an ammeter. This measures current in units called amperes or amps. If we connect ammeters into our circuit, we see that each ammeter records the same current at all places in the circuit. The current is not used up by the circuit components. Clearly, each circuit device does receive something from the current to make it work. This something is energy. Energy changes in electrical circuits. The battery acts as a store of chemical energy. Inside the battery, chemical reactions occur that convert stored chemical energy into electrical energy. The battery supplies an electrical current to the circuit. This current carries the electrical energy to the circuit devices. Each device performs an energy change. The lamp converts electrical energy into light and heat energy. The buzzer converts electrical energy into sound energy. The motor converts electrical energy into kinetic energy. A battery is a collection of cells. Cells are usually joined together one after another, positive to negative. In this way, each cell drives the current in the same direction. We say that the cells are connected in series. Each time a cell is added, the current flowing increases. This in turn increases the energy delivered to the circuit. What will happen if one of the three cells is reversed? Two of the cells will act against one another, cancelling each other out. The circuit will behave in the same way as a single cell, and a current of 2 amps will flow. Series circuits. In a series circuit, each component is connected one after another. The same current flows through each component. Each bulb is equally bright. Each receives the same energy per second from the current. The energy provided by the battery each second is shared equally by both lamps. The current in the circuit is, however, only 1/2 of that obtained with a single bulb. The two bulbs in series glow much less brightly than the single bulb. A variable resistor can be used to control the current in the circuit. If the resistance is increased, less current flows and the bulb glows less brightly. Parallel circuits. In a parallel circuit, the components are connected side by side. Each bulb now glows at the same brightness as a single bulb. The current drawn from the battery has doubled so that each bulb glows at its normal brightness. If we place ammeters into the circuit, we can see that the current divides equally through both lamps. The circuit behaves as though the bulbs are acting independently of one another. Switches can be placed into the circuit to control the two bulbs individually or together. When switch S is closed, the circuit is complete. Both bulbs glow brightly. If switch S2 is opened, bulb 2 goes off. If switch S3 is opened, bulb 3 goes off. There are 4 magnetic materials: iron, steel, nickel and cobalt. If a steel bar magnet is allowed to swing freely, it will come to rest pointing magnetic north-south. The pole facing north is called the north-seeking or north pole. The opposite pole is the south pole. If a south pole is brought close to the suspended north pole, attraction occurs. A north pole causes repulsion. Opposite poles attract. Like poles repel. Around a magnet, a magnetic material experiences a force. This region is called a magnetic field. The shape of the magnetic field can be determined by using a small magnetic needle that always aligns itself along the field line. The lines are called field or flux lines as they appear to flow between the poles. The direction of the field is from north to south, the direction of the force on a north pole. Where the flux lines are close together, the field is strong. This occurs near the poles. Two like poles repel because the field lines between them push apart. Two opposite poles attract because the field lines pull the poles together. A strong electromagnet can be made by winding a straight wire into a coil. This coil is called a solenoid. When the switch is closed, a current flows through the coil, creating a magnetic field. Unlike a bar magnet, a very strong field is created in the center of the coils. The direction of the field can be predicted by holding the coil in the right hand. If the fingers point in the direction of the current, the thumb will point to the north pole. The strength of the electromagnet can be increased by increasing the current through the coil, increasing the number of turns in the coil, winding the coil on a soft iron core. The soft iron core greatly intensifies the field. We can use this to make very strong magnets. The soft iron easily loses its magnetism. If the switch is opened, the current and magnetic field disappears. Soft iron is used to make strong temporary magnets. Steel is a hard magnetic material. If a piece of steel is inserted into the solenoid, it becomes permanently magnetized. Steel is used to make permanent magnets. Lifting heavy objects. The current is switched on to energize the magnet. When the current is switched off, the magnetism is lost and the car falls. The electric bell. When the switch is closed, a current flows to energize the coil. This attracts the soft iron strip and the hammer strikes the bell. When the contacts are broken, the current switches off. The strip is pulled back by the springy metal to close the contacts once again. The bell sounds for as long as the switch is pushed. The relay. High-power electric motors require large currents. A switch in such a high-power circuit would be very dangerous. With a relay, we can use a low-power circuit to switch on and off a high-power device. When the switch is closed, the electromagnet becomes energized. The electromagnet attracts a soft iron rocker, closing the contacts of the high-power circuit. When the switch is opened, the electromagnet demagnetizes and the rocker returns, opening the contacts. The circuit breaker. Providing the current is small, the circuit breaker will not operate. Current will flow continually. If the current becomes too large, the coil becomes energized. This attracts the rocker, opens the contact and breaks the circuit. To reconnect the circuit, the spring must be reset manually. The electromagnetic lock. With the switch open, the bolt is in place and the door is locked. When the switch is closed, a current flows to energize the coil. The coil attracts the bolt, unlocking the door. When the switch is opened, the coil expands, forcing the bolt outwards and locking the door.